Section 10.5, changes of state. So there's one video problem that goes along with this, video problem 56, so check that out after we get done. So we are going to be applying these intermolecular forces. So let's real quick go over those intermolecular forces. If the molecule is nonpolar, it has London dispersion forces only, and we know that the number of electrons determines the strength of those intermolecular forces, right, of that London dispersion force. If it's polar, you can have London dispersion and dipole-dipole, right? And still, we're looking at the number of electrons that's going to determine the strength. And we can also say something that I didn't mention last video: the more polar it is, also the stronger the dipole-dipole force of attraction. Okay? And then if it's polar and it has a hydrogen bound to a nitrogen, oxygen, or fluorine, well, then it's going to have hydrogen bonding. Okay? And again, even within hydrogen bonding, the number of electrons or the number of possible hydrogen bonds that it can form, both of those affect the strength of that hydrogen bond. Okay? So what we're talking about here is disrupting those attractive forces, disrupting those intermolecular forces. And we want to cause a change of state. In other words, we want to melt something. We want to take it from a solid to a liquid. Okay, and we all know what a solid looks like on the molecular level. We're usually talking about a very orderly arrangement, right? And it's a three-dimensional structure, of course. Then a liquid, if we're going to do a liquid, it's going to look more like this. Okay, so what does it take to go from solid to liquid? Well, we have these really strong forces of attraction that occur between all of these particles. Those should be dots. And then we need to weaken those so that the particles can move around. And how do we weaken them? Energy. We put energy into the system. Okay? So here are some terms that you probably need to know. From a solid to a liquid, it's called melting. From a liquid to a solid, it's called freezing. From a liquid to a gas, vaporization. Gas to liquid, condensation. Gas straight to solid, deposition. Solid straight to gas, sublimation. Okay. An example of sublimation is, one example is freezer burn. So you'll have ice crystals form on meat in the freezer, and then it'll turn straight into gas. Another example that they often give, of course, is dry ice, which is just solid carbon dioxide. You don't see the liquid carbon dioxide; it goes straight to the gas. Okay. An example of deposition is hail. So there's water vapor up in the air, and the water vapor, which is a gas, condenses and becomes a block of ice, basically a little thing of ice. Okay. You can also see what's going on with energy. In order to melt something, we have to put energy into the system. In order to vaporize something, we have to put energy into the system. Okay, so that's going to be important, whether energy is going in or energy is coming out. And we'll talk about what that energy is being used to do. Okay, so solids melt to become liquids. Liquids freeze to become solid. When you add heat to a solid, it makes the molecules move faster, and that action of making the molecules move faster, that's what weakens the force of attraction. Think about you and a friend that all of a sudden you both get busy doing different things and you don't hang out around each other as much as you typically do. Okay, so you have this energy that's being put in, you're moving around a lot more, that force of attraction is no longer there. So when we reach the melting point, the movement of the molecules is enough so that it weakens the attractive force. Right? So here's what I was talking about. Here's this solid, rigid structure. Right? Here's that solid, rigid structure. If we put energy into it, these guys are going to move around a lot, and they're going to become a liquid. And so once they do that, the structure isn't as rigid as it was. And this is huge. During melting, the temperature remains the same. So we often use ice, right? Because we all know that ice melts at 0 degrees Celsius. So here's a chunk of ice. And if I were to measure the temperature of that ice, while it's melting, so there's the water that's melting, while it's melting, that ice will not change from 0 degrees Celsius. Okay, as soon as it starts melting, it'll remain the same temperature. But yet I'm putting energy into it still. Well, all of that energy is being used to make the molecules separate. Okay, if we remove heat, we basically have the opposite process. When the molecules are strong enough, they'll become organized and rigid because that force of attraction is there to keep them in place. Right? And again, during freezing, temperature remains the same. Now the heat of fusion, which is often shown as the delta HF, not where F is for fusion. Okay, we already looked at delta H before. The heat of fusion is the amount of energy it takes to, in this case, they're saying 1 gram. So it's the amount of energy it takes to basically melt 1 gram. So go from solid to liquid. So here is solid ice. It takes 334 joules of energy to convert 1 gram of ice to 1 gram of liquid water. And that heat of fusion, it can be used as a conversion factor, and you'll see in the sample problems how that happens. Okay, now since there is no change in temperature, that means we cannot use our earlier equation that we used with energy, which is Q equals mc delta T, because this delta T is going to be 0, which means that it looks like there's no energy going into it. Well, we can't use that equation. We have to instead use an equation that looks like this. Q is equal to, in this case, mass times the delta HF, and that's if delta HF is in joules per gram. Take a look. If your delta HF is not, then you have to use N times delta HF, and that's when your delta HF is in joules per mole. So this is a mole right here. Now let's go ahead and take a look at this problem, because I don't really have any problems like this on the video problems. Ice cubes at 0 degrees Celsius with a mass of 26 grams are added to your soft drink. How much heat will be absorbed to melt all the ice? So let's just look at that. How much heat will be absorbed to melt all the ice? Well, we know that we have 26 grams. Right? And we know that the heat of fusion of ice is 334 joules per gram. So that means 26 grams are going to require a certain amount, 334 joules per gram. And I actually don't have my calculator on me, so let's go ahead and try this the other way. So it's 334 times 2. Let's see, 334 times 2 is 668, right? So it's 6,680 for 20 times 334. What would be 6 times 334? Let's see, 6 times 334. 6 times 300 is 1,800. 6 times 34 is, let's see, 6 times 30 is 180, 224. So that's 2,024. So $8,704 joules. Check it, because I don't have a calculator on me. I'm not going to check it myself, but that's what I got. So I checked it. It's actually 8,684. I wonder where I went wrong. Oh, this is 204. There's where I went wrong. Okay. Right, moving on. So we talked about melting. Let's talk about boiling, vaporization or condensation. So liquids evaporate or boil to become a gas. And again, we're looking at, we still have these intermolecular forces here that are fairly strong because they're liquids, so they're really close to each other. Now what we want to do is completely break those intermolecular forces and get the molecules to separate from each other. Now this takes a lot more energy. So what that means is that the delta H vaporization will always be much larger than the delta H fusion. Okay? So a couple different processes here. We have evaporation and then we have boiling. Let's talk about that. Evaporation, molecules at the surface only, when they have enough energy, they can leave that surface. And why they have to have enough energy is because they have to break those attractive forces. This is kind of like Red Rover, if you ever played that. Red Rover, Red Rover. So here's the, let's say here's the surface. The person gets to the surface. If they have enough energy, they can break through the surface and become a gas. Okay? Now evaporation is a cooling process. The reason why it's a cooling process is because remember what temperature is. Temperature is, at least in Kelvin, it's the average kinetic energy. Right? So if only the fastest particles are leaving, only the fast ones are leaving, that leaves behind all around slower particles. Right? So that makes the average drop because there are slower particles, which means lower in energy, which means lower temperature, which is why evaporation is a cooling process. Okay, so that's evaporation. Evaporation occurs below the boiling point. Okay, at the boiling point, that's when vaporization occurs, which is boiling. Below the boiling point, it's called evaporation. And below the boiling point, only the surface can evaporate. At higher temperatures, all molecules can overcome the attractive forces and become a gas. So if we're looking at, let's say, here's a pan of water. It's a very good pan. So here's the water itself. So evaporation only occurs along the surface here. But boiling is when any molecule within this, so even these molecules here, can become a vapor. And so what happens is the molecules inside here become a vapor, and they form a little vapor bubble, rise to the surface, and then escape. Freedom! Okay. So what we're talking about here is the amount of energy it takes, so that's the heat of vaporization. And again, we already talked about the heat of vaporization up here. It's huge compared to the heat of fusion. Here, if we take a look, we can see some examples. Here is water. The heat of fusion, in other words, to melt 1 gram of ice takes 334 joules. To vaporize 1 gram takes 2,260 joules. That's a huge difference. Take a look at ammonia. To melt it, 351 joules. To make it turn into a gas, 1,380 joules. Why so much more energy? Because remember, for the heat of fusion, all we're doing is we are weakening those intermolecular forces. Right? So we are going to weaken those intermolecular forces, IMF. Right? Vaporization, we are going to break those intermolecular forces, which takes a lot more energy. Okay. We can also say that the type of attractive force determines the heat of vaporization or fusion. So here, take a look at this. We have propane and benzene down here at the bottom, which are nonpolar. Take a look at their heat of fusion. Very small heat of fusion, right? Then we get into polar. Take a look at the heat of fusion. Then take a look at the heat of vaporization. Right? For these hydrogen bonded particles, it's huge, very large. And then of course we compare that to ionic, which ionic is many, many times stronger than our intermolecular forces. And so we see that it takes a lot more energy for that to happen. So what we can do is we can set up a lab and we can measure the temperature as energy is being put in. So in other words, let's say we take some ice. It's boring, but we take some ice, measure the temperature. It starts out at, let's say, negative 40 degrees Celsius, so it's in a really, really cold environment. And we take that ice, so there's the ice, and we just put a Bunsen burner underneath it, okay, in order to put energy into it. What we'll see is that the energy will increase until it gets to about 0 degrees Celsius, and then we'll see a plateau. And that plateau is where it's changing from a solid to a liquid. So we have both the solid and the liquid existing at that plateau. But notice that the temperature, here's the temperature doesn't change. So what's going on at that plateau? Well, at that plateau, we are weakening the intermolecular forces. So the energy is not being put into the kinetic energy, the energy is being put into the potential energy, which is the energy that's stored in those attractive forces. So over here, where we have melting occurring, that's where we are weakening the intermolecular forces. Okay? Remember, temperature is the average kinetic energy, so if the temperature is increasing, the average kinetic energy is increasing. So in other words, we're making the molecules move faster and faster. Here, temperature is not increasing, therefore we're not increasing the kinetic energy, the average kinetic energy. What we're doing is we are weakening those intermolecular forces. And then we get to the point where they all become weak, and then the temperature increases. And then we get to the point where we're no longer increasing the temperature, but now we are breaking the intermolecular forces. Look, this line, which signifies the amount of energy added, is much larger than this line, right? So here's line A, here's line B. Line B is much larger than line A because it takes a lot more energy to get it to turn into a gas than it does to get it to turn into a liquid. Okay? So anytime we have a change in temperature, we can calculate how much energy that is by looking at Q is equal to msh delta T. Okay, or if you're going to be an AP, Q equals mc delta T. Now, on the horizontal lines, no change in temperature, so we can't use Q equals m shot. Okay, we can't use that. Instead, on the plateaus where there's no change in energy, we have to use Q is equal to mass times delta H, either fusion or delta H vaporization. Now that's as long as your delta H is measured in joules per gram. If it's measured in joules per mole, obviously use moles. A cooling curve is basically the opposite process. All right? And here I go over with you if we want to calculate the total energy, and this is what the video problem is on. We're going to use Q equals msh delta T whenever the temperature changes, and then Q is equal to m delta H when the temperature is not changing, when there is a plateau.